This is lesson 4.6 on negative and zero exponents. The content of this lesson is kind of just additional to the unit. It has nothing to do with vertex form or factored form or parabolas. It's kind of just an added lesson that has to go somewhere, so it's on the end of this unit. Okay? It will relate back to a little bit to what we've done already, but mostly it's totally new and it's just one lesson. The first thing I'd like to do is point out the difference between two types of functions. We know that the standard quadratic function is y equals x squared. Y equals x squared. In this example, this is a power, x squared is a power, where x is the base and 2 is the exponent. And we can draw a quick sketch of that on our first graph. It's just a parabola, goes through 0, 0, symmetrical on both sides. That is a quadratic function being graphed. What we're going to tackle today has to do with exponential functions. We're not actually going to talk about exponential functions, but we're going to use this just to show you the difference. So now it's also expressed as a power, but instead of having the base be our variable and the exponent be our constant, the base is a constant, or is a value, and the exponent is the variable. So you can see the difference right away. So automatically, don't get mixed up between something that looks like this, what we have in pink, y equals 2 to the power of x, and something that says, like we have in orange, y equals x squared. This graph looks like this. One-sided. Actually, that's not really actually a good drawing. I'm going to redo just part of that. Okay. So there you have a comparison between the graph of y equals x squared, which is a quadratic, and y equals 2x, which is exponential. Today we're going to be tackling questions about this type of equation right here. We're going to do so through an investigation. In order to get a good idea of what an exponential relation looks like and what it does and what is the meaning of negative and zero exponents, we can use patterns. So go ahead and copy and complete the list that I'm drawing. So we're going to look at what 2 to the power of 5 is, then 2 to the power of 4, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, 2 to the power of 5. Well, that just means I'm doing 2 times 2 times 2 times 2 times 2. 2 times itself 5 times. So you could kind of count it in your head. 2, 4, 8, 16, 32. So 2 to the power of 5 equals 32. But what about 2 to the power of 4? It's just one less factor of 2. 2, 4, 8, 16. Go ahead and complete the chart. Okay, you should be able to look up and have the same numbers as me. Now what I want to ask is, how did we get from here to here, from here to here, from here to here, from here to here? What did we multiply one of the terms by in order to get the next term? We divided by 2, which is the same as multiplying by a half. So what we really did is we multiplied by a half, multiplied by a half, multiplied by a half, multiplied by a half. So we've identified a simple pattern. But what if that pattern had to continue? On this side, my exponent is going down by 1. 5, 4, 3, 2, 1. The next one is 0. What's my next exponent? Negative 1. Then what? Negative 2, then what? Negative 3, and we could keep going. I'm going to stop there because I'm out of space. But you could keep going all the way down to negative 5. Now, this pattern also continues. In order to get the next term, we need to multiply the previous term by a factor of 1/2. So what happens if we take the number 2 and multiply it by a half? It's basically just saying 2 divided by 2. It's 1. What happens if we take 1 and we divide that by a half? Just get a half, right? Half of 1 is a half. What happens if we only have a half of something? Let's picture a pie of some sort. We only have a half of it, and we're going to cut that half in half. Now how much do we have?
A half of a half.
A third.
A half of a half,
A third.
which is
A quarter.
a quarter.
He had it as a third. Wow. Just put that. Wow.
It would only be a third if all of the pieces were equal in size. It's a quarter whether I draw the last dotted line or not. Now let's consider one of these quarters, and we're going to cut that in half. Make sure it makes sense to you. Now we have an eighth.
So you're basically just multiplying the bottom number by 2?
You're basically just multiplying the denominator by 2, which, look, here's the denominator. 2. Top times top, bottom times bottom. We're multiplying the denominator by 2 in every single case. You go ahead and fill in for 2 to the power of negative 4 and 2 to the power of negative 5. Okay, we're going to use that table of values now to draw a graph. Okay, so you need a y-axis. Are any of our values negative? Our x values are, right, but not our y values? Our x values can go negative, so we need to make sure we have some space left and right of the y-axis. But we don't need to go deep into the negative y's. So you should have a sketch. Looks a little bit like this. We're dealing with x values from negative 5 to 5. And now all we're going to do is plot every single point that we have. The highest point that we made was 32. So I'm going to put 40 at the top of my y-axis. The next point, 2 to the power of 6, would be 64. So you can see how fast it's growing up in these numbers. But for the sake of our drawing, we only went from x values of 5 to negative 5. And our greatest value was 40. And now we want to carefully plot our points. So when x was 5, we were at 32. Where x is 5, we're up here at 32. Where x is 4, right, because this is y equals 2 to the power of x. So where x is 4, we're at 16. It's down about here. Where x is 3, we're at 8. Down about here. Where x is 2, we're at 4. That's down here. Where x is 1, y is 2. It's getting closer and closer to the x-axis. What about where x was 0, y is 1? Where x is negative 1, we're down to a half, and then a quarter, and then an eighth, and then a 16th, and then a 32nd. So we're getting closer and closer and closer and closer and closer and closer to the x-axis, but we're not touching it. Go ahead and draw a curve of best fit. So a curve that takes all of your points into account. Looks pretty straight at the beginning. Then as we cross through the y-axis, it starts to curl up. And then it starts to curl more and more and more and more and more.
Without a line of best fit, let's show the points.
a curve of best fit and a line of best fit do not have to touch all of the points, but this curve happens to touch all of the points because it's actually based on one specific function, not random data that we plugged in, right? So we know that the curve follows that shape specifically. All right, somebody tell me something about that curve. It goes up eventually, yep. Anything else? Any?
It's half a parabola.
It kind of looks like almost half a parabola, right? If it started going back up right about there, it would start to look like a parabola. But it's not. It's not a parabola. It's different. Good. Anything else? Anything about its rate of increase? How fast is it going up? How slow is it going up?
Doubling.
It's doubling every single time. When we're dealing with negative exponents, does it grow very quickly?
No.
Not at all. But what about when we start dealing with positive exponents?
It grows very quickly.
It grows very quickly, right? It's slow right around here, but once it crosses x 2 to the power of 1, which was just 2, by the way, just the same as the base, 2 to the power of 1 is the base. After that, it grows really rapidly. Will it ever cross the x-axis?
No.
Nope. Good job. What do you think this graph would look like if instead of dealing with y equals 2 to the power of x, what if we dealt with y equals 3 to the power of x? It would be tripling every time. So would it grow more quickly, or it would grow way faster? What about in the negative numbers? It would be even smaller than these numbers, because you'd be dividing by 3 each time going backwards, right? Multiplying by 1/3 each time. Would it ever cross the x-axis? No, it wouldn't. So it might look like this. It might be underneath the pink line till here. Anything to the power of 0 is 1, so they would cross at that exact same point. And then up here, 3 to the power of 1 would be 3 instead of 2. And then it would be at, instead of 2, 4, it would be at 2, 9. Instead of 3, whatever we had here, 3, 8, will be at 327. Okay, and then 4 will be at 81. Those are just the multiples of 3. And it looks more like that. So that's what an exponential function does. It grows very slowly, and then once you cross 0 and 1, it grows very, very quickly. Now, the reason that we did that is so that we could get this chart, and so that we can make some connections there, and we'll do that next with some of our laws of exponents. I'm going to clear this board in just a second so that we can review some of our exponent rules. But before I do, I want to draw special attention to this section of the chart right here. Okay? In here we have 2 to the power of 0. Notice that 2 to the power of 0 does not equal 0, right? Because the graph never touches 0. So it couldn't possibly. But what we're going to describe by the end of this lesson is why 2 to the power of 0 equals 1. And part of that explanation is right here. Because if you go down your powers, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, this value is just getting multiplied by a half. It's just getting multiplied by a fraction. So it can never get to 0. It just gets multiplied. This pattern continues from 2 to 1 to 0. This pattern continues from 4 to 2 to 1 to a half to 1/4. So it's one explanation for this. Why 2 to the power of 0 equals 1. We're going to get the other one right now. Exponent laws. Exponent laws. We already know a couple of our exponent laws. We actually know 3 of them from 4.0 Getting Ready. We reviewed all of our exponent laws. Does anyone remember any of the laws of exponents? I can give you a hint. We had the product rule.
Oh, factor by factor by factor. Never heard that. How'd you know that?
The product rule states that if you have any base, let's say the base is x, and you raise it to a power of a, and you're multiplying it by more x's, let's say x to the power of b, so you have a x's and then b x's, and you're multiplying them together. What do we do? Yeah, good job. We add our exponents. X to the power of a plus b. So just a quick example of that. If you had x to the power of 2 times x to the power of 5, you would end up with x to the power of 7. Another one we had, very related to the product rule, is the quotient rule. Product has to do with multiplication. Quotient has to do with division. The quotient rule states that if you have any power, let's say x to the power of a, and it's divided by another power, but that second power has the same base, so that base is x in both cases, what do I do to my exponent here?
Subtract.
This is the same as x to the power of a minus b. So a quick example, if we had x to the power of 6 and we were dividing it by x to the power of 3, the numerator here would just be x times x times x times x, 6 x's, and the denominator would be x times x times x, 3 x's. Well, the 3 in the denominator can cancel out 3 of them in the numerator, so we know that this should just be x to the power of 3. And look at what happens. We take x to the power of 6 minus 3, which equals x to the power of 3. Another helpful law of exponents. The third law of exponents that we learnt is the power of powers law. You can do it underneath or off to the side, however you're making use of your space. I'm going to write it right here. Power of powers. And it's called that because you have a power, like x to the power of a, and you're raising it to another power, say b. How do I simplify this?
X and then a times b.
X to the power of a times b. Let's take an example. Let's say we had x to the power of 3, and we were going to raise that to the power of 2. X to the power of 3 means you have x times x times x, right? If we take that to the power of 2, that means we have it 2 times. We have x times x once, and then we have x times x again. Which really just means we have x to the power of 6. 3 times 2 is 6. That's a good summary of our exponent laws. Okay, in order to get a little bit of practice with our exponent laws and to get a better understanding of how they work, we're going to do a handful of examples really quickly. Okay, we're going to do a handful of examples. We're going to start with this expression, 3 to the power of 2 divided by 3 to the power of 5. Now, if we're going to expand that, that means we're going to show what's actually happening in the numerator and the denominator. What does 3 to the power of 2 mean?
3 times 3.
It means 3 times 3. What does 3 to the power of 5 mean? 3 times 3 times 3 times 3 times 3. Make sure you double check that you have 5 factors of 3. Well, let's say this 3 cancels out this 3 cancels out this 3. So in the numerator we're left with 1. And we have 1 over 3 times 3 times 3. We're going to say that's 3 to the power of 3. Which exponent law did we use? It's the quotient law, quotient rule, right? So now this is how it looks if we expand and divide. And let's look at what our quotient law says. It says that if we have 3 to the power of 2 over 3 to the power of 5, which we have, right? It says that we can do our base 3 to the power of 2 minus 5. What's 2 minus 5? So we have 3 to the power of negative 3. After we do a few of these, you're going to see a connection. I'm sure you're almost already seeing it. We started with the same expression in both cases. Here we ended up with 1 over 3 to the power of 3. Here we ended up with 3 to the power of negative 3. Okay, so you should already be able to see a connection. Go ahead and draw a line underneath that one. We're going to do a second one. We're going to do 4 to the power of 1 over 4 to the power of 3. Well, if we expand that one and divide it out, the numerator is just 4 once, and the denominator is 4 times 4 times 4. Two of these 4's cancel out, one in the top, one in the bottom, and we're left with 1 over 4 squared. Well, let's see what happens if we apply our exponent law for the quotient rule of exponents. Starting with the same expression, 4 to the power of 1 over 4 to the power of 3. Our quotient rule says that's the same as 4 to the power of 1 minus 3, which is 4 to the power of negative 2. Go ahead and draw a line. We're going to do one more of these so that you get an idea. Let's say our base isn't a positive number. Let's use a negative number. Let's use negative 5 to the power of 3. And it's going to be divided by the same base to the power of 7. That's going to be really annoying. Let's not do that one. It's too long. Let's do it. So in the numerator here we have negative 5 times negative 5 times negative 5. And in the denominator we're going to have negative 5 times itself 7 times. So go ahead and draw that out in the denominator and make sure you have negative 5 7 times, all multiplied together. I'm using brackets. I think it's clean and simple and easy. And once you have that written out, you can say some cancellation. Well, negative 5 over negative 5 is just 1, so those cancel out. Negative 5 over negative 5 is just 1, so those cancel out. Negative 5 over negative 5 is just 1, so those cancel out. So in the numerator, we're just left with 1. And the denominator, what do we have?
1 over the power of 4.
Negative 5 to the power of 4.
Negative 5 to the power of 4. Let's jump over to the exact same expression, but using our exponent law. We've got negative 5 to the power of 3 over negative 5 to the power of 7. Our quotient rule says that that's negative 5 to the power of 3 minus 7, which reduces to negative 5 to the power of negative 4. Can you have negative exponents? Apparently, yeah, you can. They're right there. Okay? What is the connection between negative exponents and positive exponents? They're reciprocals. Very good. Okay? There's a connection there. Excellent. Let's write a brief note on the bottom.
That's it?
That's not it. That's it for our chart. But we're going to write a note underneath the chart. Okay? When a non-zero based base is raised to a negative exponent, when a non-zero base is raised to a negative exponent, the result is the reciprocal of the base raised to the positive of the exponent. When a non-zero base is raised to a negative exponent, the result is the reciprocal of the base raised to the positive of the exponent. So one quick example, just so you have it there. Okay, one quick example. If you have 2 to the power of negative 3, that's going to be equal to the reciprocal of the base, that's 1 over 2, raised to the positive of the exponent. Instead of negative 3, we have positive 3. And that's the relationship between positive and negative exponents. Okay, your second table is going to be the exact same as your first table, but we're going to be talking about a different set of expressions, but we're going to use the same exponent law. So in this case, we're not going to talk about one exponent being bigger or less than the other exponent. We're going to deal with a situation where the base is the same and the exponent is the same. 3 to the power of 5 over 3 to the power of 5. Now let's see what happens if we expand and divide this. In the numerator, we have 3 times 3 times 3 times 3, 5 times. And in the denominator, we have the same. 3 times 3 times 3 times 3 times 3. Make sure you have it 5 times in each. Now what happens when we start canceling out some of these 3's in the numerator and the denominator?
It's going to be 1 over 1.
It's just going to end up being 1 over 1, which is equal to 1. Okay, let's try the same thing but using our exponent law. If we have 3 to the power of 5 over 3 to the power of 5, our quotient rule for exponents says that that's the same as taking our base of 3 and taking our exponent from the numerator, subtracting our exponent from the denominator. Well, 5 minus 5 is 0. See what just happened there?
So it's just going to be...
It's helping you understand that any base to the power of 0 is not 0. It's 1 every single time. And here's why. Because they would cancel out, and it actually is 1. It's not like a weird math thing that they just put in so that we have a way of dealing with it. It actually really happens. Let's try another one. Okay? Let's take the base negative 2, and we'll raise it to the power of 3. And we're going to divide by negative 2 to the power of 3. In the numerator, we get negative 2 times negative 2 times negative 2. And in the denominator, we get negative 2 times negative 2 times negative 2. What happens when we start canceling all these things out? We get 1 over 1, which equals 1. Negative 2 divided by negative 2 is 1. Negative 2 divided by negative 2 is 1. Negative 2 divided by negative 2 is 1. Let's apply our quotient rule for exponents on the exact same problem. Negative 2 to the power of 3 over negative 2 to the power of 3. Our rule for exponents tells us that we can do negative 2 to the power of 3 minus 3, which means we have negative 2 to the power of 0. What have we discovered about any base raised to the power of 0?
This one is going to be 1. Always 1.
Any base raised to the power of 0 is 1. Quick example. X to the power of 0 equals 1. Another example. Negative 47 to the power of 0 equals 1. Let's try a couple examples quickly. Example 1 gives us 5 opportunities to use our new exponent rules and to make sense of them. The first one is fairly straightforward. It says 4 to the power of negative 1. Now, what do we know about negative exponents? A base raised to a negative exponent is the exact same as the reciprocal raised to a positive exponent. So 4 to the power of negative 1 is exactly the same as 1 over 4 to the power of 1, which is just 1 over 4. So 4 to the power of negative 1 is 1/4. B gives us the question 8 to the power of 0. Emma, what do you think? It's just 1. Any base raised to a exponent of 0 is just 1. Alright, let's get a little trickier. C. C gives us negative 2 raised to the power of negative 3. What do you think we do with this first? We could, expand it out, but we don't really know what it means to expand something to the power of negative 3. It's not the same as negative 2 to the power of 3. So what do we need to do first? We have a negative exponent. What did we do with this negative exponent? We made it the reciprocal with a positive exponent. Let's try it. So this is going to be the same as 1 over negative 2 to the power of positive 3.
Wouldn't the negative, or wouldn't the base be positive 2?
So far, all we've done is one step. We took this with a negative exponent, where this is the base, right? You just have to picture this as being x to the power of negative 3.
Yep.
And now it's 1 over x to the power of 3. That's all we've done so far. Okay? X hasn't changed at all. The base hasn't changed yet. But now we can use Isaiah's strategy, and we know how to expand this, right? We still have 1 in the numerator. The denominator could be negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is positive 4 times negative 2, negative 8. So we have 1 over negative 8. And if we wanted to simplify that properly, we don't want a negative in the denominator. So this is just negative 1 over 8. And I can do that because a positive divided by a negative is a negative. Okay? Good. Let's look at D. D is a little bit more challenging because it uses a fraction. So you're getting a little bit of every kind of example here. Again, raised to a negative exponent. So D is 2/3 raised to the power of 2. What do we do when we see a negative exponent? We use the reciprocal raised to the positive power. So the reciprocal of my base is what? Yeah, instead of 2 over 3, it's going to be 3 over 2. And instead of having a negative exponent of negative 2, we're going to have positive 2. Here's a very important rule for you to remember when you're dealing with exponents and fractions. 3 over 2 to the power of 2 means that the numerator and the denominator get squared. Okay? This exponent applies to the numerator and to the denominator. So this is, in the numerator, 3 times 3, and in the denominator, 2 times 2. Both of those values are getting squared. Oh, yep. Okay? So here we're left with 9 over 4. The last example here is E. E is 0 to the power of negative 2. Now the 0 is not in the exponent, it's in the base. And we have a negative base. So what even happens here?
0.
You might be tempted to say that it's 0, but let's look at what happens if we write it as a reciprocal. What happens to this as we write it as its reciprocal? We get 1 over 0 squared. What do we say about any expression that has 0 in the denominator?
Undefined.
Ah, way to go, Jonathan. Lindsay almost said it. Undefined. Okay, it's not 0, it's not 1, it's not anything. It's undefined. It can't be done, it doesn't exist. It's a nothing statement. It's undefined. We have no way of expressing it. Okay? All right, example 2 is an application of our exponent laws that we've been learning about, negative and zero exponents. It has to do with radioactive decay. So if you know anything from science class about radioactive decay, let's say a living creature dies and it has carbon in it. Okay? Carbon decays at a certain rate exponentially. It's exponential decay, and they can take a measure of the amount of carbon that's left in the decaying material of that animal and determine how long ago that animal died. Okay? Doesn't work super accurately sometimes, but here we go. We are given carbon 14. So I'm just going to write down some notes that summarize the problem. Carbon 14 is a radioactive element that decays to 1/2. It decays to 1/2, or 2 to the power of -1, right? That's the exact same as 1/2. Carbon 14 decays to half of its amount.
Is it minus 14?
Carbon 14, carbon dash. Decays to 1/2 of its amount every 5,700 years. Okay, this is called the half-life of carbon 14. The half-life of carbon 14 is 5,700 years because the amount gets cut in half every 5,700 years. So if you start with 40 pounds, after 5,700 years, you'll have 20 pounds. After another 5,700 years, you'll have 10 pounds. After another 5,700 years, you'll have 5 pounds, 2.5 pounds, 1.25, etc. Okay? Our question is to determine the remaining mass of 10 grams of carbon 14 after a certain amount of time. So determine remaining mass. Determine the remaining mass of 10 grams. So we know how much we're starting with. 10 grams after A, 11,400 years. 11,400 years. Okay, well, let's look at this. We know that for each 5,700 years, the original amount decreases by a factor of 1/2. How many of these 5,700 year periods fit into 11,400 years? It's simple math, right? We just have to divide 11,400 by 5,700, and we'll get that then it will be cut in half 2 times. Okay? So let's do that. We show that 11,400 divided by 5,700 equals 2. So that means we're going to have 2 half-life periods. That means that the amount of 10 grams is going to get cut in half 2 times. Okay? So the amount that we started with is 10 grams, and it's going to go through 2 half-life periods. So this fraction, 1/2, represents 1 half-life period. If we do it by 1/2 again, we get 2 half-life periods, and that's exactly what this exponent means, 1/2 times 1/2. Let's see what happens here. We have 10. We're going to deal with our exponents first. 1/2 squared means 1/2 times 1/2. Top times top, 1. Bottom times bottom, 4. So here we have 1/4 times 10, or 10 divided by 4. You can check that in your calculator. It's 2.5 grams. So if there were 10 grams of carbon 14 in some sample, after 11,400 years, there would be 22.5 grams. Now it seems silly to talk about it that way, but now look at it in reverse. If you found a sample of something that had 2.5 grams in it, you could estimate that when it was alive it had 10 grams. Then you could look backwards and say, okay, I know that it must be approximately 11,000 years old. Which is ridiculous, but that's how carbon dating works.
Our world is only 6,000.
Okay,
2017.
Here we go. B. It's the exact same question, but instead of 11,400 years, we're going to look at 28,500 years. So even a longer time span here. The math is the same. We have to figure out how many half-life periods have happened here. One half-life period is 5,700, so we're going to divide that out. You can use your calculator there to figure out that it is 4 half-life periods. So that means that we're taking our mass of 10 grams and our half-life period. This time I'm not going to express it as 1 over 2.
It says 5.
I'm going to express it. Sorry. What?
Exactly.
It says 5. It says 5 in the calculator.
4. No, it's 4.
Yeah, no, you guys are right.
Calculators are smart.
You guys are right. It's 5. Okay. This time, instead of using the fraction to express a half-life, I'm going to use this 2 to the power of negative 1 to express the half-life. Okay, so don't be confused. Instead of doing 10 times 1/2 to the power of 5, I'm going to do 10 to the power of, 10 times 2 to the power of negative 1 to the power of 5. So we have our original amount. This expression means half-life, and this is saying that we're going to have 5 half-lives. Using our rules of exponents, that means 10 times 2 to the power of negative 5, which means 10 times 1 over 2 to the power of 5. 2 to the power of 5 was 32. So we have 10 over 32, which you could put in your calculator. And I don't have the answer because the book was wrong on the number of half-lives.
Okay.
But it'd be 10 over 32. And you can put that in your calculator. Grams are left of the 10-gram sample that we started with. So after 28,500 years,
It's
you have
0.3125.
0.3125
Yeah.
grams. Good, thank you. Your homework is the worksheet. Do your best. Look at your notes. There's a lot of notes. Lots of different things are said here. Go ahead.